This is Daniel Coosbury, and we're going to try to finish up our study of descriptive statistics with a few more numbers that we can use to describe data and data sets. And this particular set of numbers we're going to call measures of position, which are going to focus on looking at a data set as a whole and picking out one or two values and talking about where does that value lie in the data set. Like if we've got 100 values and we pick out one, we want to talk about with respect to the whole data, like not just as order, but you'll know what I mean in a sec. But like where does it compare with most of the data or some of the data? Is it in the majority? Is the majority of data around it or not near it? So these are kind of things we're trying to talk about when we talk about position. So I've got three of these to show you in this video. The first measure of position we're going to look at is called a z-score, and we're going to use a z-score to answer this question. So we've got a man who is 73 inches taller or a woman who is 68 inches tall, and we want to answer the question, who is taller? Well, there's an obvious answer. The man is taller than the woman. However, if we're interested in, with respect to their own gender, which of these individuals is taller in that regard? So is the man taller compared to most men, or is the woman taller compared to most women on average? We're going to use the z-score to try to figure this out. Yep, we're going to use the z-score to figure this out. So this is what a z-score is. The z-score tells you, first off, the z-score refers to a particular data point. So unlike the mean and the standard deviation that talks about all the data, each data point can have its own z-score. So we're just talking about one data point, like 73 is how tall the man was. The z-score of 73 is blank. So we're looking at just one data point. Tells how many standard deviations away from the mean that data point is. So if you have your data, if you know what the mean is and you know what the standard deviation is, you're going to plug in your data point as x. So this is where that 73 or that 68 will go. You subtract the mean, divide by the standard deviation, and then this tells you how many standard deviations away from the mean the data point is. So this definition is important to remember and understand, because you're going to see questions like, how many standard deviations is this number from the mean? What it's asking is, what's the z-score of this number? But what it's not saying is, what's the z-score? It's saying how many standard deviations. So we need to start associating this number of standard deviations from the mean with this new term, z-score. Okay, so let's answer this problem. We need the mean and the standard deviation to find a z-score. So here's some data for the population mean of men's heights. So there it is. There's the population standard deviation of men's heights. So we want that, and we want that. And then we have the mean height for women, and we have the standard deviation of the height for women. So when we do that, we can find the z-scores for each number now. So we're going to treat those as our mu's and our sigmas. This is an x in our formula. There's one data point. This is also an x. So we're going to do the formula twice. We're going to find z for men, for this man's height. We're going to find z for this woman's height. Okay, so z for the man's height is going to be x minus mu divided by sigma. So you see where those numbers come from? X minus mu divided by sigma. And you get 1.16. So that's a z-score, just some number. I don't think it has units. I think it's just a number. The units are gone, which is why we're going to use the z-scores to compare one thing with another thing. They can be different scales, kind of like the coefficient of variation. Okay, z-score for the woman's height, she's 68 inches tall. There's the x. Minus the mean for women divided by the standard deviation for women's heights, and you get 1.5. So then we can say, relatively speaking, so relative to the population, the woman is taller than the man because her z-score is bigger. When you subtract the mean divided by the standard deviation, she's tall for a woman, or she's taller for a woman than he is for a man, is something you can say. So the z-score is really nice for comparing things like that. It standardizes things. It's kind of like the coefficient of variation. And you can describe, you can kind of compare particular data points in different populations maybe. So for instance, in the population of men or the population of women, we can compare the x's. Whereas earlier we couldn't say, well, 73 is taller than 68, but that's not really the question we're trying to answer. So the z-score is real powerful for talking about where something lies in a data set. The next thing that you've probably seen before that talks about where something lies in a data set is called a percentile. So a percentile divides the data into hundredths. So imagine taking a data set and dividing it into even 100 pieces. And for a number p between 1 and 99, the pth percentile separates the lowest p percent of the data from the highest 100 minus p percent. Okay, let me try to say this a different way. So p can be any number from 1 to 99. So we can have a first percentile, a second percentile, a third percentile, a 50th percentile, or a 99th percentile, any of those numbers, any of those counting numbers between 1 and 99. The pth percentile, so let's just say that p is 30. The 30th percentile, for instance, separates the lowest 30% of the data from the highest 100 minus 30 or 70% of the data. So the 100 minus p suggests kind of like an opposite. So if we're doing percentages, the opposite of 30% is 70%. If I were to do 40%, the opposite would be 60%, and so on. So don't get freaked out by these letters. This is what this is saying. Separates the lowest 30%, if it's the 30th percentile, from the highest 70%, or so on. So we talk about percentiles a lot when we're doing test scores and things. So you want to be in a high percentile. You want to be above 95% and maybe less than 5%. You don't want to be below 95%. You want to be really high. But we can find percentiles for really anything. You don't even need to have 100 pieces of data to do something like this, and I'll show you. So we have below, I have this housekeeping data. So these are the amount of times it takes for the housekeeping personnel to clean a certain room. So some people can clean it really quickly in like 9 minutes, and some people can clean it more slowly in like 18 minutes. We want to find the 80th percentile in this data set, which means we want to find the number that separates the lowest, and I'm just guessing here, the lowest 80% of the data from the upper 20% of the data. And I'm just guessing based on this picture that 80% of the dots are over here, 20% of the dots are over here. I just made it up. It could be that it stops here or it stops here. But the idea is we want to know which one of these numbers, is it 8, 9, 10, 11, 12, or so on, separates the lowest 80% or the highest 20. So I'm going to guess it's around 15, but I don't really know. We're about to find out. It could be 16 or 14. But you see how I've tried to capture 80% of the dots and leave 20% of the dots. So there's some number on this scale. It's probably 14, 15, or 16 that's going to separate 80% and 20%. We'll call that the 80th percentile. It's also called P80 with a little 80 down there. So a little P and then even a smaller 80 down there is what we're looking for. So here's the steps to finding percentiles. And you also use this to find quartiles, which we'll talk about later. So I'm going to ignore that for just a second. So to find the pth percentile, we're going to first arrange the data in order, which I kind of did when I made this dot plot. So I have the 8s, there's 9s and 10s and so on. But you want to arrange them in order because we're talking about where it is in a data set. And the data set needs to be in order from least to greatest. And then if n is your sample size, for the pth percentile, we're going to find this number. So this is a neat little formula that's going to tell us the location of the pth percentile. So this L stands for location, meaning which number is it? Is it the first number in the data set, the third, or the fourth, or so on? What's the location of that percentile? And then these are quartile things I'll show you later. And then if L is a whole number, we're going to take the average of the number in position L and position L plus 1. So these are locations. I'll show you this when we do an example. If L is not a whole number, you're going to round it up to the next whole number, and that'll be the percentile. So maybe I'll talk about this in a sec, but this is really what's going on is this is kind of like finding the median. So, you know, when you're looking for the median of a data set, sometimes it's just one number. You can just pick the number. Sometimes you got to average two numbers together to get the median. We saw that if the data set's even. So the median is like smack dab in the middle. This is like we're looking for a percentile that's 80%, you know, on the right 80%. But depending on the size of the data set, sometimes you just pick a number, just round up to a number. Sometimes you got to average numbers like the median. That's all I'll say about that for now. So let's use these steps to find the 80th percentile. So step 1 is put your data in order. There it is. Step 2 is we're going to find the location of the 80th percentile. I think it's worth writing again. This L stands for location. of the 80th percentile, or P80. So I'm going to plug in 80 here, and my sample size is 30. So there goes 80 and 30. So do 80 divided by 100 times 30, and you get 24. So the location of the 80th percentile, for that, I got 24. Now, maybe this isn't the best way to say it, because now I got to go back to that first slide and say, okay, if L is a whole number, which is what happened, the pth percentile, or the 80th percentile, is the average of the number in position L. I got 24 on my example. And position L plus 1, which would be position 25. I know this is kind of frustrating and confusing. This is just the method to find it. It's like for the median, you got to take the two middle numbers, not just one middle number. So here we got to take the number in position L, which is the 24th number, and the number in position L plus 1, and average them. So in my data set, I want to find the 24th number. I'm going to count back from 30. 30, 29, 28, 27, 26, 25, 24. So that's the number in the 24th location. That's the number in the 25th location. So I take those two things and average them. It's just how you do it. Okay, so P80 is the average of those two numbers, which is easy to average. 16 plus 16 divided by 2 is 16. So my 80th percentile is 16. Okay, so let me talk through that process again. You want to sort your data first. You find the location, and this is not the percentile. A lot of people, just do the math and say, this is my percentile 24. But 24 is not even anywhere in my data set. What you want to do is you want to find the 24th thing and the 25th thing and average them. And that'll give you your percentile. So what that means, graphically speaking, remember I said I wanted to separate 80% of the data from the upper 20%. So this is 80%. And this is 20%. So earlier, I think I drew my line here. Turns out it goes right here. So this is my 80th percentile, is this number 16. So that means that this should be, all these dots should be 80% of the data, where all these dots, I've just ruined this graph, should be 20% of the data. So when I say the 16 is the 80th percentile, I'm saying that everybody who has, or 80% of the people have cleaned less than this person, or faster than this person. 20% of the people have cleaned slower than this person, these 5 people. So I don't know, if you're working for a huge company and you're trying to be more efficient, maybe you want to find who's in the upper 20% of, this would be the slowest, but we'll say it's the upper 20%. And say, well, okay, well, those 20% are cleaning it slower. Let's, I don't know, retrain them in how to clean some things more efficiently or quicker, and then see if they improve. But we can leave these people alone because these 80% of the people are cleaning much better than these 20%. That's kind of how this works. So we can find for any number between 1 and 99, any whole number, we can find percentiles using this method. So I would hang tight to this slide, because this is the method for finding any percentile. And it's a little complicated, but the math itself is not terribly challenging. Okay, so we also might get a data point and be asked what the percentile is. So instead of saying what's the 80th percentile, we might be given a data value and say, well, like if the number's 16 in my 16 minutes in my last thing, what percentile is that? We're going to use these steps to answer that. So we're going to take the number of values that are less than that plus 0.5 and divide by the number of values in the data set. So these are also helpful steps. I'm just going to show you the example. The following table represents the annual rainfall in inches in Los Angeles over several years. One year, the rainfall was 1.90. What percentile is this? So in this whole data set, what percentile is the number 1.90? Is it high on there? Is it not high on there? I can look and see, okay, well, there's a lot of data points. This looks like it's not halfway, so halfway would be the median might be here. I'm just guessing. You wouldn't ever guess, but I'm just guessing. So this might be 40%, might be 42nd percentile. I don't really know, but I have a method to do that. So my formula said I need all of the values that are less than 1.90, and then all the values total. So I can count all the values that are less than 1.90. Since they're in order, I just count all these things and end here. And I get 18 things. So that's where that number comes from. And then I've got 45 things total. So according to this formula, the number of values less than 1.90, that's 18. And the number of values in the data set is 45. And then you just plug these numbers in. So 100 times 18 plus 0.5 over that, and you get 41.1. Now the last step of this was to just round that to the nearest number. So unlike that first slide where you round it up, we're just going to round this to the nearest whole number, which, oops, that's not right, which is 41. Round it to the nearest whole number, and I'll say this is the 41th percentile, or I could call this P41 if you wanted to. But that's how you do it. So there's two questions that we just did. The first question was, what's the 80th percentile? So I don't know what the number is. It's one of these numbers. The other question is, which percentile is this number in the data set? And we'd say it's the 41st percentile. Okay, so percentiles are messy, but you use the exact same process to find any percentile in any data set. So once you practice with a few, hopefully this will get a little more comfortable. Now, there's something called quartiles, which is much easier to work with than percentiles, because quartiles divide the data set into 4 pieces instead of 100 pieces. So that's where the word quartile comes from. Quart, 4, divides it into 4 things. So the first quartile is called Q1. It separates the lowest 25% of the data from the highest 75%. We can also call Q1 the 25th percentile. So quartiles are percentiles. They're just special ones. So this one divides the lowest quarter from the highest 3 quarters. The second quartile divides the lowest 50% from the highest 50%. That's also called the median. So we've actually learned what this is already. We just have a new word for it. We can call it quartile 2. The third quartile separates the lowest 75% from the highest 25%, and we can think of Q3 as the 75th percentile, or P75. We can think of this as P50. They're all the same thing. Q1 and the median, Q2 and the median and P50, they're all the same thing. But quartiles are nicer than percentiles, I think, because most things know how to find quartiles already. So one thing we like to do is we like to describe a data set using the minimum, the maximum, and 3 quartiles. And so we present 5 numbers that describe the data set, which I'll have to show you in another video. But quartiles aren't hard to find. In fact, so here are either the exact same instructions for finding percentiles. But since Q1 is the first the 25th percentile, and Q3 is the 75th percentile, then I would just add to these steps. If you're looking for Q1, let P be 25. If you're looking for Q3, let P be 75. And then just follow these steps to find the quartiles. Now I'm going to show you how to find the quartiles another way, because the TI-83 and the 84 can find them really easily. And you already have actually done the work to find them. I just haven't showed them to you yet because it hasn't been time. So let me take the cleaning data and show you how to find the quartiles in my TI-83-84. So here's what I've done. I put the cleaning data in my calculator. I went ahead and sorted this because I was using it for something, but this is the same cleaning data as that are on this slide. And I'm going to get out of here and do the one variable stat thing again. So this is the same thing we've done for mean and standard deviation and variance. And I'm going to calculate that with L1, keep frequency list blank. And I get this readout. Now don't touch anything, just look at the readout. See how there's an arrow down here? If you press your down arrow, it'll show you more things. Look at that. It'll show you the minimum, it'll show you Q1, the median, which is Q2, and Q3, which is 15, and the maximum, which is just the biggest number. So it'll tell you the min, the max, all 3 quartiles. It just calls it the median, which is really all we need for the quartiles. So here's what I would do. If I'm finding quartiles for a data set, I'm not going to do it the long way like I would for percentiles. I'm just going to use my calculator and get the quartiles that way. So I got my 3 quartiles here for the cleaning data. So that means, oops, I'm off this. So that means if I'm looking at the cleaning data on a histogram, or my dot plot, they work very similarly. I can say that this is the lowest 25% of the data. And this is, the median's 13. So I could say that this is also 25% of the data. And then from 13 to 15, this is also 25% of the data. And then from 15 to 18, this is also 25% of the data. Now I've overlapped a little bit because there's a lot of, there's one thing here, but there's a lot of things here. And so some of these might go in here. But that roughly splits the data set up into quarters, which is really nice. And it helps describe the spread of the data a little bit, but it shows you kind of the location of certain numbers. Like, does it fall in the middle 50% or the upper 25%? So the middle 50% would be like this one and this one together. The lower 25%, you could talk about the lower 50%. Finding quartiles is really powerful because you can say a lot of things just from having those numbers. But I might have to save that for another video because this one's kind of running out of time. So those are the 3 ways of measuring position of something. You can use a z-score, you can use a percentile, or you can use a quartile. And I'll talk about more of what to do once you find the position of things in another video.